Two notes. The homework keys are posted to our Canvas page. Should be at one of the lower modules right above class stands, I believe. So you have the opportunity to go back and say, well, this is what I came up with. What was he looking for? What did I do that was different? If you've got questions, come talk to me. I will be glad to discuss the assignment with you in any detail. Secondly, remember that the lowest single homework assignment is thrown out. So if one of these went off, don't worry about it. Meanwhile, let's talk about continuity. One of the reasons we like the limit laws is that they allow us to establish an idea of what it means for a function to be sufficiently nice. I hate that term. But it's original. Both Leibniz, Newton, Gauss, Euler, Fermat, all of the mathematicians who developed this stuff in more detail were the ones who said this only works for a function that's nice. Now, to Newton, a function was nice if he could draw it without lifting his pen. I think that's one of the stupidest definitions I've ever seen. I wish I was making this up. Now, he wrote it in Latin, but still, same idea. That's garbage. This is a useless definition. So, later analysts said, what I need to do is I need to figure out what this really means. And eventually we came up with the idea of looking at our limits and where limits were nice and worked and where they didn't. Consider, I think the problem was in chapter 2, section 2, where you had the graph and you had to ask all these limits and the value questions. I think it was h of x as we approach -3 and as we approach 2 and as we approach all of these different values, right? Most of the time, the idea of the limit as we approach a and the value at a are related. And the discussion we had with that problem was that there were several places where those two things weren't related. So let me grab one of the pictures from chapter 2, section 2. Go back to that particular problem. Yeah, here we go. Here's our picture. As we approach 2, from either side, we have a limit as x approaches 2. Because from the left, as we get closer and closer to, our y values get closer and closer to, well, it also looks like 2. As we approach from the right, same thing occurs. We get closer and closer to a y value of 2. So I have a limit. It works. But what's my problem? There's a hole in the function, dear Liza. It's screwed up. There's a hole there. There's no dot. So my relationship broke. On the other hand, if I look as we're going towards 0, do I have a limit? As we approach x equals 0. I got some people nodding and some people shaking their heads. There's a question here. Grace, tell me, you were shaking your head yes. That just tells me there's a value at 0. If I plug 0 in, I get out the value 1. That's the dot. But a limit means I'm not looking at 0. I'm looking at what happens as I come into 0. Aha. As I come in from the left, I'm going towards 1. But as I come in from the right, I'm going towards -1. So I actually don't have a limit at 0, even though I do have a value. The fact that I don't have a limit gives me a problem, right? I have to lift my pen. I had to lift my pen to jump over 2. I had to lift my pen to jump from being up here to being down there. I had to lift my pen. This is a problem. And so people were able to take this rough idea about being nice, not lifting your pen, and actually figure out what we need is the relationship between a limit and a value. So I'm going to define this property called continuity by looking at these two ideas. A function is continuous at a point, x equals a. I don't care what the y value is, provided 3 things occur. So this is my foundational definition. A function is continuous at the point x equals a, if and only if. The hell does that mean? It means if I say something is continuous, all 3 of these things hold, and if all 3 of these things hold, then that thing is continuous. Works both ways. 1, we have a limit at the point a. 2, we have a value at the point a. There's got to be a closed dot somewhere. 3, those have to match. As we just saw, it's possible to have one or more of these conditions fail. And graphically, this is fairly easy to identify because of that. If I don't have a limit, then one of the things that we saw in that picture we were just looking at has to be true. We have to have a hole. There'd be no value for f of a. That would violate property 2. We have to have a failure to have a limit. Here, page 115, figure 2. I'm going to look at what happens as we get closer and closer to 1. Do I have a limit as x approaches 1? From both sides, the left and the right, we're getting closer to whatever that y value is. Perfect, I have a limit. That's property 1, check. Property 2. Does f of 1 exist? There's no dot. There's a hole in the picture and there's no dot anywhere to be found. Property 2 fails, I'm done. Function is not continuous at 1. What about at 3? I don't have a limit because from the left I'm negative, from the right I'm positive. I do have a value. There is a dot down at the bottom there. F of 3 exists, so property 2 is fine. The property 1, out we go. What about at x equals 5? I have a limit. Property 1 is fine. I have a value. Property 2 is fine. But they missed each other. Property 3 fails. So I have a limit, I have a value, but the limit and the value don't match. These are the possible visual interpretations of what it means for each of my properties. Now, this is not the only way to have no limit. Remember, we had that oscillating bit in picture in chapter 2, section 2. It's possible to have the limit not exist on one side. It's possible to have the limit not exist on both sides. It's possible to have the limit exist on both sides, just fail to match up. So there are lots of different ways to have the limit fail, but the value must match that limit result. Questions? 115. I don't know what that means yet. There are 3 places where this function fails to be continuous: 1 and 3 and 5. There are different kinds of not continuous. We'll talk about different kinds of not continuous in a minute.
Or is it fair to like think when you're thinking of a limit that's like coming in for a value like vertically?
Yes, the value is there a dot above that x or below that x? So we think of a value as if I drew a vertical line, would I touch the function? You're welcome. More questions? I like this as the image in my head. Jumps, gaps, holes, those are my problems. But that's what it looks like graphically. How do I know from a formula? Most of the time, when I'm looking at a function algebraically, it's easier to figure out where continuity fails rather than where continuity is existing. So most of the time, what I'm going to look at is, where did one of my rules fail? So let me start with them in a slightly different order than the textbook definition. I find looking at limits to be more convoluted than looking at values. Let me start with value. Is there a place where if I plug in a number, this function goes up yours? If I plug in 2, what happens? Bottom is 0. I don't even care about the top at this point. I know the bottom is 0. This function is undefined at 2. As far as I can tell, that's the only value, the only x, where I fail to have a y value. That means that all other x's are part of the domain of this function. Okay, hustle back to our limit laws section. The direct substitution property. When did we say the direct substitution property worked? We gave 2 types of functions it worked for. Say again? Not just linear functions, we have a much more broad category. Polynomials and rational functions. There was more to that phrase. In the domain of those functions. Polynomials and rational functions have limits by direct substitution as long as the bottom is not 0. And if I'm using direct substitution, then I'm saying to look at the limit, you can just plug the number in. Isn't that what condition 3 says? That the limit and the value have to match. The direct substitution property basically says that every polynomial is continuous everywhere, and every rational function is continuous except at the points where the bottom is 0. So that's the only place where this function is not continuous. Now, Emily, you said something else about this function. Not just the bottom being 0, but the numerator is 0 also. When I saw 0 over 0, my brain went, something's wrong here. I should do some algebra to try and figure out what's actually happening at that point. There could still be a limit as we approach 2, even if there isn't a value. They're independent ideas from one another. I can have a limit and not have a value. Remember, we saw the graph come together, but there was still a hole in the graph. That's fine. That's the value failing, not the limit failing. I'm going to change this function. My new function g is the same as f everywhere except 2. And at 2, I've decided the value is 7. That's okay. The original equation didn't have any value there at all, so I could make one up. 7. Is this function continuous at 2? Why not, Evan?
Because the f of the a value is somewhat different with the doesn't match the limit.
Well, I don't know that. What is the limit? I didn't compute the limit yet, did I? I need to know what that limit is. So now my question is, what is the limit as x approaches 2 of g of x? Because if that does happen to be 7, then I worked it out. That's where the hole was going to be, and I just plugged the hole. But I don't know what that limit is. Did I plug the hole correctly? A rational function like this, in order for me to simplify it, I should see if I can cancel something with that factor on the bottom. That'll get rid of the 0 over 0 part. So let's factor the numerator. I want two numbers. When you multiply them together, you get -2. When you add them together, you get -1. I need to make sure that one of them is negative to get the -2, right? -2, +1. Oh, so that'll cancel. And this will become just the limit of x plus 1 as x approaches 2. And that is 3. You're absolutely right, Evan. I didn't plug the hole properly. What I have in this graph is a value that I say, oh, we should be going towards 3, but the actual value is 7. Oops. So in spite of having a limit and having a value, I fail condition 3 because the two don't match. If I had picked 3 instead of 7, then yes, I would make a continuous function. Let's call that function h. This function is continuous at 2. And therefore it is continuous everywhere else, because all of the other x values are in the domain of the rational function that is the top part of h of x. So what I've done is I've taken a function that was discontinuous because it had a hole in it, and I've managed to plug the hole. I've turned a discontinuous function into a continuous function. Any type of discontinuity that I can do this to is called removable, because I can fix it in some fashion. 99.9% of the time. Knowing that a discontinuity is removable does you no good. In this class, there are classes later where knowing that something is a removable discontinuity is useful. We'll save that for those classes. I just wanted to mention it to you here. Questions? If that's a removable one, what's one that's not removable look like? If my limit is going to fail to exist, we'll do this as a piecewise function again. I'm going to define this to be 1 over x for all the values except 0. Oh, and when you put 0 in, you get out 2. Talk to me, Jordan. If I put in 0, I get 2. But what's the limit as we approach 0? Why? Why does this limit not exist as we approach 0? But I could fix that, right? I tried to fix it. I said, I don't care about 0 being on the bottom of the fraction. You're not actually plugging in 0. You're only looking at what happens as you get close to 0. When you plug in 0, you get out 2. I fixed that part. But what's the limit as x approaches 0? Why? Why does this limit fail to exist at 0? Aha. If you pick a very small negative number and take 1 over that, you get a very big negative number. If you pick a very small positive number and take 1 over that, you get a very big positive number. We've got a vertical asymptote at 0 that I decided I was going to put a dot in at 2. But as we approach from the left, we go to a minus infinity. And as we approach from the right, we go to positive infinity. Different values from different sides doesn't exist. my left-hand limit and right-hand limit are different. Even if the limit from each side was the same, we'll change this function just a little. J of x is 1 over x squared if x is not 0, and 2 when x is 0. Well, now the limit as we approach 0 does exist, because I'm squaring the numbers. What happens to a negative number when you square it? Which means I'm going to get a very small negative number squared. It's going to become a positive small number. Take 1 over that, you're going to get a positive big number. So as I come in from the left, I get positive big numbers. As I come in from the right, I get positive. Those are both going to positive infinity. But remember, infinity is not a number. It's an idea. So, can this ever be equal to f of 0? F of 0 is 2. 2 is definitely not infinity. Property 3 failed on me again. It is possible I could have something that oscillates back and forth, like sine of 1 over x, that looked like a seismograph, and that would give me another failure of a limit to exist. I could have limits, and it would still fail. Here's a function. This function is called the floor function. It's also sometimes called the greatest integer function. Now, the floor function is very weird, because the floor function spits out the greatest integer less than or equal to your number. Now, that sounds convoluted, but really what it means is that this thing rounds down. Somebody give me a number that is not an integer. 4.1. The floor of 4.1 is 4. The floor of 6.937 is 6. The floor of 2 is 2. The floor of pi is 3. It always spits out an integer. The floor of negative square root of 2. Decimals. Somebody tell me, what's the decimal for the square root of 2? Perfect. 1.4 is all I really need at this point, but it's negative. I got to go down to an integer that's negative 2. If I gave you negative 4.1, then the floor would be negative 5. We're going down to the next whole number. Always going down. So let's think about the graph of this. if you give me a number between 0 and 1, a half, 2/3, 5/16, 73/95, whatever, any number between 0 and 1, what is the output when you stick it into this function? 0, because they're all 0 point something, right? So they're all going to give me a here, except for what happens when you put in 1. It's up at 1. So there's going to be an open circle right here. What about the numbers between 1 and 2? They're all going to give me the same thing. But when I get to 2, we're going to jump up to 2. Between 2 and 3, the same thing will happen. Between -1 and 0, and between -2 and -1, I get the same effect. This function has limits everywhere. As you approach 1, there's a limit from the left and a limit from the right, but they're different. Limit doesn't exist. There's a jump at every whole number. This is really, really, really not continuous. It's not continuous at every whole number. I hope to no one's surprise, this is called a step function. You've seen lots of step functions, even if we haven't called them that. If you order something that doesn't qualify for prime shipping, you have to pay for the shipping, right? When's the last time you actually ordered something that didn't qualify? Never. But if you don't get free shipping, you've got to pay for the shipping. And they charge you shipping based on how much you spend, right? You spend less than $10, you're going to pay this much. Between $10 and $40, you'll pay this much. Between $40 and $60, you'll pay more than 100, then we'll make it free. Whatever their setup is, but it's steps all the way across. A function that is made up of a bunch of pieces of horizontal lines is called a step function. There are functions that are infinitely more discontinuous than this. Really can mess with your head. If you're interested, I recommend you look up a function called the Devil's Staircase. It's related to something called a Cantor set. Has nothing to do with Devil's Tower, the place where Close Encounters of the Third Kind movie happened. But it's called the Devil's Staircase. It's an interesting function. Questions? Say again. Okay. The domain of my function, square root of x, you can't put negative numbers into a square root. We get complex numbers. We're not dealing with complex numbers here. So we can only put in numbers that are bigger than or equal to 0. All the numbers, including 0, going off to infinity. Is this function continuous at 0? It clearly has a value at 0. Square root of 0 is 0. Why? Why does the limit fail to exist? The function only exists on the right-hand side of 0. I don't have a limit at 0 because I can only come from one side. Okay, wait a minute. Let me go back to the definition of being continuous. The limit has to exist, the value has to exist, the limit and the value have to match. What if I took the two pieces that involve the limit and said, let's only use the limit from the right? Then this would work, wouldn't it? Because the function only exists on one side. So we can talk about being continuous from the right or being continuous from the left if we take our two places where the limit showed up in the definition and make them both limits from the right or both limits from the left. And that is perfectly acceptable. When we look at a function with a limited domain, it is much more helpful to us to really only consider that side of our limited domain. Knowing where my function is not continuous is very important, but I don't want to rule out points where the function really doesn't even exist on the other side. The best part about this is that since continuity behaves like limits, my limit laws carry over. If two functions are continuous and I add them, the sum is continuous. Subtract them, the difference is continuous. Multiply them, multiply one of them by a constant. Divide them as long as you're not dividing by zero. Perfectly fine. As a matter of fact, all of the nice functions we work with, page 120, are continuous at every point where they are defined. Polynomials are defined everywhere. Perfect, they're continuous everywhere. My favorite kind of function. Rational functions, as long as I'm not dividing by zero. Root functions, as long as I'm not worried about an even root of a negative number. Trig, tangent, secant, cosecant, cotangent. They all had places where they were undefined, but everywhere else, perfect. Inverse trigs, same deal. Exponentials, logarithms. Logarithms. Where were logarithms undefined? The thing inside the logarithm had to be bigger than zero. Not bigger than or equal to, but strictly bigger than zero. Which means if I look at this disgusting thing in example 6, logarithm of the inverse tangent, logarithm of x plus the inverse tangent of x divided by x squared minus 1, bleh, I can figure out which points to throw out based on this idea. All I really need to look at is domains, which is an algebra concept that shows back up in calculus and beats us over the head with it. X squared minus 1, if I was dividing by 0, I'd be in trouble. Where am I dividing by 0? Square root of 1, plus or minus 1. I have an inverse tangent. Inverse tangent. Okay, people, dig back into the trig banks. That's tangent. Inverse tangent is the function that undoes tangent. We called it the arctangent sometimes in the trig class, as opposed to just calling it tangent to the minus 1. But it switched x and y in the graph of tangent. All right, wait a minute. Time for the math dance. What's the graph of tangent look like? Come on, straight lines, parabolas, absolute values. What's the tangent look like? Y'all took trig, don't make me go get Miss McNabb. Or Mr. Nichols, or whoever your trig teacher was. Graph of tangent It's like this. It's got an asymptote on this side and an asymptote on this side, but it swoops up and down in between those two asymptotes, which means the inverse function twists that. And it goes all the way out to the left at this asymptote and all the way out to the right at this asymptote and is defined everywhere in between. And that means that the inverse tangent is defined from minus infinity to infinity and is continuous everywhere. If you're looking at me like I'm a space alien, go back to Appendix D where all of our trig stuff was. The graph of the inverse tangent here it is in the reference pages in the back of the book. What about that ln of x? Because that was the other part of this function. Ln of x only allows in positive things, which means I have to have x be bigger than 0. I need all of these conditions to work at the same time. Tangent of x doesn't, inverse tangent, doesn't care at all. It has to be bigger than 0, and it can't be 1. It could be anything between 0 and 1. It could be anything from 1 to infinity. It can't be anything 0 or smaller. And now we figured out where this is continuous. I can add, I can subtract, I can multiply, I can divide. I can put one function inside another. It's called composition of functions. Down here at the bottom of page 120. If f is continuous at some point, and g is continuous at the y value of f, then I can plug f into g. Composition not only preserves my idea of continuity, it enhances it. There's a really nice consequence to having continuous functions. When I draw them, I'll go back to Newton. When I draw them, I don't lift my pen. Here is a cubic function. Cubic function is a polynomial. What do we know about a continuity of polynomials? They're continuous everywhere. Plug in 1, plug in 2. Tell me what you get. Those of you grabbing your calculator should probably go ahead and graph this equation as well. Yes? I claim somewhere between 1 and 2, this function has a root. There is a cubic formula, like a quadratic formula. There's a formula for solving cubic equations. Niccolo Tartaglia and Girolamo Cardano came up with it in the 1500s. I don't know it. I don't want to know it. It's a pain in the ass. I'm not going to deal with it. But I claim there's a root between 1 and 2. How do you know I'm not talking out my ass? I didn't lift my pen, right? I went from negative values to positive values. Somewhere I had to cross the x-axis. As a matter of fact, I claim somewhere between 1 and 2, there's a value where the y is equal to 6. Somewhere there's a value where the y is equal to 10 or negative 0.5. It has to cross every possible horizontal line between these two y values. Between. The intermediate value theorem. If I have a function that's continuous on a closed interval, it includes both ends. If f is continuous on AB, and the ends have different y values. Then, for every value between f of A and f of B, there is an x value, x equals c, with f of c equal to n. There could be more than one, but there must be at least one. I'm not going to prove this. The proof is not very long, but I want you to draw me a picture. Draw a pair of axes, put A and B somewhere on there. Draw f of A and f of B. I don't care if f of A is smaller or f of B is smaller. Then draw a horizontal line. Connect f of A to f of B without touching that line. You can't do it. But this only works because of continuity. One of the homework problems will ask you, is it possible to do this and have it work if f is not continuous? And the answer is, yeah. It's also possible to make it fail when f is not continuous. And you should have to draw pictures for both. I will see you all. Have a wonderful rest of your day. If you came in late and I still have your homework, come get it. It's the easiest way for me to take attendance today.